Well, you must be. I still have three students, I think, who are pending. So let me take this opportunity to suggest that you look through your emails. Make if you are not in the course, it is because you haven't responded to the email sent by Canvas. So check your emails, look for something from Canvas or Instructure, and there will be a link in there for you to join your course. You need to get in here if you're not in here. If you don't know how to get in or you're having troubles, give me a call, 405-684-6828, and we'll get you in this thing. So I just thought I'd drop in another little video. There's a lot to cover here and a lot of unwritten things in the chapter I noticed that we want to talk about. But for now, let me get back over to the textbook. Uh, nope, there we are. Okay, so in the introduction, I don't want to read this chapter for you, but we'll be talking about Pascal's law and pressure and flow are defined and explained, as well as positive and negative pressure. That negative pressure is pretty much the inlet of a pump or vacuum. Uh, there's some organizations that I want you to know about that govern several things, standards such as ASME uh, and, of course, OSHA and institutions such as that. So I'm not going into this little exercise right here. I want to get on into some things that I need to clear up just a little bit, I think. So we're in the introduction part. The prime mover. This is a cascading system. That means you have something doing something to something else, which in turn does something to something else in turn and turn. And so efficiency is of great concern because if your component, one of those components is lacking, then it affects the rest of them. So uh, the prime mover could be an electric motor. They're using, and most of your heavy equipment is a diesel engine and or some other internal combustion engine. Moving toward electric power, though. So the let me start the sentence. The machine's prime mover, typically a diesel engine, but could be an electric motor or other types of internal combustion engine, is used for power input to drive the system's pump and consequently the actuator or the cylinder, as we're more familiar with, like the lift cylinder on a loader or the dump bucket, the dump cylinder, or a motor such as like the subject we won't go into very much, but is hydrostatic drive. That's rotary motion. We'll touch on that. And the power output of the hydraulic system is the actuator. Hydraulic fluid is used to transfer energy throughout the system. We'll get more definitive when we get to Pascal's law. So let's see. So a lot of people think hydraulic system as a fluid power system. However, technically, pneumatic or gas is also a system, and it's also considered a fluid. Fluids are divided into liquids and gases. They both are known to occupy whatever container you pour them in, and Pascal's law will apply to both of them when we get there. And I'll let you read some of these things. There's some really good figures in here about brakes and things that could be that are demonstrating multiple force multiplication. Let me just talk about flow and pressure. Flow and pressure work together, and they're managed by a system of components to achieve the design parameters set by manufacturing engineers. And these parameters are based on values that a machine needs to achieve, such as lifting things, digging, etc., etc. The maximum values are limited by prime mover horsepower, for one thing. Uh, the hydraulic system design, in other words, what is your PSIs max on all your hoses and things, and your adjustments, your valves, and structural strength of machine components, such as the arms itself, like it shows you right down here, the backhoe. This cylinder up here is actuating the bucket, right? So this arm and this boom has to withstand the pressures or forces that are transmitted by digging throughout the machine, all the way down to this very important pin that's here on backhoe. Some of you may be that familiar. If not, that's okay. Fluid pressure in the system increases as resistance to the actuator motion. I just told you about that. When you start to dig, that fluid coming in here is flowing, and then it goes into that cylinder and it hits the face of that piston, and that's the resistance that it encounters, and then that's going to create pressure. So resistance to an actuator motion increases. Fluid pressure in the system increases as the resistance increases. If the system pressure can overcome the load, whatever it takes, on the actuator, motion will continue. However, if the load increases beyond maximum pressure capabilities of the system, the actuator starts moving. And if you've operated a backhoe often, you have experienced this, such as in wet clay versus loose gravel, as they used for demonstrations here. Oh yeah, loose gravel. It depends. If you're in loose gravel, there will be very little resistance and fills the bucket machine. And wet clay, if you've ever dug in that, you're going to get a lot of resistance. So properly designed system is important. I want to get into force multiplication. That's what we're all about here. And take a look at this. Is a mechanical demonstration of force multiplication. In a minute here, we'll have hydraulic or fluid demonstration of it. Look at the fulcrum situation here, where you have 100 pounds that you want to lift. So you go out here 10 feet at your mechanical advantage, and it's taken 10 pounds of force multiplied this by this distance. By the way, that's how they do backhoes to get their maximum. The further out you go, and you crane guys know this too, the more leverage to your advantage or even disadvantage if you don't want to tip the crane over. But here's the takeaway. When you move this out here, you're going to move it down so much, but you're only going to be able to move this a little bit. Although it's more, you're going to lose. So force multiplication is a trade for force here. This, you can call this a force here, for distance travel. You can lift more, but the distance you travel, and we'll get into that a little bit more with the when we get into the hydraulics. I'm coming over here. I'm going back to a little sketch I want to show you. Let's see if I can get there. Evidently, Ah, lucky me. See my hand, let me get that out of the way. This is force multiplication. This is, I ran out of room, but that's okay. It's just given. You're given 100 pounds of pressure. So we're pushing down on a piston here. And we have 100 psi. In one scenario, and which is what you don't see up here, in one scenario, you're pushing, your 100 pounds is pushing against 2 square inch diameter piston, right? So you're getting 200 pounds. You have your of force of lift with 100 pounds of psi. That's a factor of 2 to 1. Down here we have the same pressure in the same vessel, but we have a lot of a much bigger cylinder here. We have 4 square inches. So when you're able to lift 4 pounds. Now look at these 3 variables. We have pressure, we have area, and we have force. Now look up here. If you were in my grades class, it seems like a long time ago, I drew a circle that took away transpositions. When you have 3 variables and you know 2 of them, in this case force, area, and pressure, if you know 2 of these, you can find the other. Look down here. Let's take this 2 inches of area, and let's take this 100 pounds per square inch of pressure. So if we take the area 2 inches, multiply it times the pressure 100 psi, we get 200 pounds of force. Look at this example. Same vessel, same cylinder, 100 psi, or same actuators, different sizes. So you got 100 psi, but here you have 4 square inches of area. So let's do the same thing. Our area is 4. Our force is 200. So force equals area times pressure. Let's look at area here, 4 square inches times pressure here as opposed to up here, and you get 400 pounds with this. So same pressure, different area, you get a force multiplication. Again, we'll get into this. You're going to lose a little distance in your actuator. You're going to lose a little difference in that bucket. Let's say when that bucket is trying to curl and that ram is coming down here, you're going to lose a little distance here and maybe a little speed. But in this case, you'll lose half the distance as in this case, because this, you want to remember these factors. It'll take a lot of calculations away. If you look at this, you got 2 divided by 4 divided by 2. You got a 2 to 1 factor here. I believe I did that right. So you're lifting twice the amount with this increase. Of course, you double the size. Everything is relative. But that's what I wanted you to see as far as illustration of force multiplication. Let's see, do I have anything else? This is another one. It's nothing new. It's just maybe a better representation. 200 pounds. Look, 400 pounds. You're going to lift. You got 50 psi. You take the force by the area, 200 pounds, divided by the area, gives you the 50 pounds of pressure. The area, where is the area? I lost it. Oh, 4 inches. But it's the same thing we were talking about a while ago. This one kind of illustrates better that this is connecting these two vessels, and this has an 8 square inch area piston. This has a 4 square inch piston, and therefore you double your lift. But you definitely, your volume, just while I'm here, gosh, I hate that there's no end to it, but you gotta push this liquid down, and the volume never changes. But when you push down here, you may push down 6 inches here, but you're only going to get 3 inches of lift out of this piston because the volume is bigger here. Up here, this volume, it takes a whole lot more fluid to move a lot less distance. And again, you got a 2-to-1 factor. Where can I put that? 2-to-1. So if you move this 6 inches down over here, you're going to move 3 inches over here. And that's the loss you get. You gain twice as much lift power, but you lose a little bit of the actuator distance, like I was talking about a while ago. I can't seem to quit. I'm sure you're getting the idea. I want to go over, when I get there, I'll come back here. This looks like a mess, and it's not really. I may use this and not, but we've got some things that we're going to cover in the book still yet that I want to make sure I get to. So I'm going to try my luck at getting back there. Let's see what happens. Not there. Yay. So as the mechanical thing illustrated, we lost a little bit of distance. Now let's move on. Here is a clear illustration of what we were just talking about. Area, 1 square centimeter. They call it the effort. I'm going to call it this force out. They usually call that. But this is also the downward force. You're sitting 1 kilogram on this thing. You're pushing with 1 kilogram of force effort. Now it goes down here and it's coming into this larger area over here, which is 10 centimeters. So you're going to have a 10-to-1 force multiplication factor. So whatever you do here, you're going to be able to do 10 times when it comes to force, but you're going to lose a tenth. You're only going to go a tenth of this in distance. So you're going to lose a lot of distance with this. But you understand, that the fluid, that takes a lot of fluid to fill this thing up. And so you got to push this a long way to get a little ways here. But that's the way all this equipment is designed. This heavy equipment that we use. The trade-off results when the force multiplication occurs is that actuator speed and travel is reduced. Speed's a little bit harder to define, and we will get to that. But I want you to understand that there's a trade-off for this force multiplication deal. Let's go. The terminology, I'm going to let you figure it out. I just want you to know that where'd it go? I want to know, everybody knows hydrostatics. It says it refers to the study of fluid in an enclosed and tightly sealed system where the fluid is at rest and either under pressure or not. So when you have a torque converter, right, for transmission, you're taking away the mechanical aspects of the old pressure plate and the clutch situation. And the same way in a tractor, a lot of the older tractors have planetary gears, or still do, have combinations of fluid or hydrostatic drive. My little tractor is a little farm tractor. It's got hydrostatic drive. And my neighbor has an old Massey Ferguson that's the same horsepower, 35. And hers will do a lot more work than mine because, of course, mine's a whole lot easier on the on to operate, but hers will lift and or pull more than mine will. And mine's a much newer machine. Hers is a 1981, but you know, times have changed. So I want you to be able not necessarily memorize these as I've said in earlier videos, but understand them. And if you don't understand them, get in touch with me and say, I just really don't understand what they're talking about. Of course, pneumatics is anything to do with air. Uh, where am I? Advantages and disadvantages. I'm going to let you go through these. These really don't need any explanation. There's a lot of advantages, but there are some disadvantages. The hydraulic system, as you can see, you can do a lot of things in a small area, and they're flexible, unlike mechanical things. You know, you have to have pins and things. So, and I'll let it'll explain that to you. You don't need me to go over that for sure. Let's see what's next. Pascal's law. Everything we do in hydraulics and a lot of the air stuff that we do, and we have air over hydraulics. So this guy, Blaise Pascal, talked about, observed that the effects of pressure applied to a fluid in a closed system. Pascal's law states that pressure applies to a confined liquid, it's transmitted undiminished. That means it doesn't lose anything in all directions and acts with equal force on all equal areas. And that's what we were showing over here. Oh my goodness. Here, we kind of, no, I'm not going there. I'm going back. Where was it? Well, that's a fine. How do you do it? I will show it to you when I get to it. There's uh, the advantages and disadvantages, and you can figure those out after you read this. You will understand. You will need to know, be able to answer it. I think there's a test question relating to that. Back to Pascal's law. Acts with equal force on all equal sides. And that's like blowing up a balloon. Uh, like that's air, using air instead of using a gas instead of a liquid. When you blow that balloon up, you got the same amount of pressure pushing against the walls of that balloon. When you run the flow of fluid into a cylinder, once it comes in contact with that piston, which is the flat round surface, it meets resistance, therefore it creates pressure. And the pressure is equal throughout that system from that point on back to where it came from. So if I get a chance, I don't think I need to illustrate that. I think you got that. I don't want to overkill this video, but let me go. This last principle, which I've talked about, and I have a little takeoff on for a layperson in there, but this is Bernoulli, and this is really a handy deal, both in aerodynamics and in fluid dynamics. His principle states that a rise in pressure in a flowing fluid must always be accompanied by a proportionate decrease in speed, and conversely, an increase in the speed of the fluid results in a decrease in the pressure. As oil flows through a system and is made to speed up by the pump, there will be a pressure drop, and inversely, if the speed of the oil flow decreases, its pressure will increase. So it talks about a practical application of this principle for technicians would be when they are replacing a hose or tube on a machine. Care must be taken to ensure the replacement of the hose or tube is the same inside diameter as the one being removed, because everything is designed around that flow and pressure. You're going to have problems as it goes through the valve. You may have cavitation, chatter. So it says otherwise a pressure drop or increase will occur and may affect system performance. Dramatic changes in fluid velocity across a valve as it goes through may create force imbalances on the valve spool and result in erratic operation. And you may have seen that. Most people say, well, I got air in my line. Probably not. So it's probably something to do with the velocity or the flow. The flow rate is the better word for it, and that flow rate is in gallons per minute. Velocity is in it's a different ball game. So, and we're not getting there. We may yet. But I hope this helps get you well acquainted with the first little section, the first 2 or 3 little sections here, and we'll move on from there when we get into Module 3. Again, if you're having problems, be sure to let me know.